So hi everyone to our weekly seminar at the Instituto of Astrophysics in Crete. So today we have a pleasure to have with us Fran Pozuelo from the beautiful Granada. So let me share a bit about Fran first. So Francisco earned his degree in physical sciences from the University of Sevilla and moved to the Instituto de Astrofísica de Andalucía in Granada for the PhD. During that time, he conducted research on minor bodies in the solar system, comets and asteroids, focusing on understanding how comet tails form and evolve. He completed his PhD in 2014 and spent 2 years as a postdoctoral researcher between the IAS-6 and the University of Granada, during which he developed a strong interest in exoplanets. In 2016, he was awarded the Anna-Marie Sokolowska-Curie postdoctoral fellowship, which enabled him to join the TRAPPIST research team at the University of Liège in Belgium, where he soon focused exclusively on the study of exoplanets, joined the Speculus team and collaborating with NASA and ESA space missions such as Kepler, TESS, and Cheops. And then finally, in early 2023, he returned to the IAS-6 in Granada with a permanent position. He is currently part of the Carmenes team and serves as the project scientist of the photonic EMARCOT project, which is an innovative concept of a large aperture telescope with the main scientific driver of better understanding exoplanets. And so thanks, Fran, for accepting our invitation. The floor now is yours.
Okay. Thank you very much, Caro, for... Okay, one second. Okay. Thank you very much for the invitation to be here today with all of you. As Caro said, I'm coming from the Instituto Astrofísica Andalucía in the south of Spain. Let's start. I'm having some problems with the timing of the clock. Okay, now it's working perfect, so I can measure the timing. Okay, so thank you very much, as I mentioned, to be here today with all of you and your interest in this particular field of research. I'm going to talk to you about the great diversity of exoplanets. And I hope you find interested. At the end, if you have any questions, I will be very happy to answer and to discuss and debate anything that can call your attention. I'm going to turn off my camera to avoid any problem with internet stability, and then I can open again later. Okay, so this is the outline I'm going to focus today. First of all, I will start making a short description of how to find exoplanets, just in some particular methods only. I'm not going to describe all of the methods that currently exist. Then I'm going to focus on what we call the great diversity. And this is something that we learn from the link between the exoplanet field and the solar system studies and knowledge that we have stored over the decades of exploration of the solar system. And we have found that there is an extreme diversity of exoplanets and planetary exotic configuration that were never expected. So we will talk about that. And then if I have time enough, I will spend a bit of time in two particular planets or system that has been discovered recently. WASP 193b is what we call the cotton candy planet. It was a discovery paper that we published last year. It's fascinating because it's a very strange planet. And then the TOI 2267 that I call the impossible system, and you will see that it's a planet that challenged the formation theories of planetary formation that currently we have. So let's start with how to find exoplanets. So I don't know how many of you are familiar with the techniques that we have to find exoplanets. So the point and the thing that is important to remark is how difficult is it. So imagine a firefly that is actually orbiting a house light. So imagine how to try to disentangle the light coming from the firefly when the house light is on. It will be extremely difficult because of the contrast. I mean, the house light is much more bright than the firefly. So actually it's in between a million and 10 million times fainter, the firefly. So actually this is the typical example that it uses to explain this important point, because it's very similar to what happened with planets and stars. It's very difficult because the planets are so weak in comparison with the star that we are totally blinded by this brightness coming from the star. It's an extremely challenging task to disentangle the lights coming from a planet that one's coming from the star. But still, the human being is amazing, extremely creative, and there are some methods that allow us to see the planets, to really see the planets. This is the method that we call direct imaging. And its concept is very simple, is to try to mask the light coming from the star with some kind of a coronagraph. It's a mask that we put over the bright part of the image coming from where the planets are. And then when we reconstruct the image, we can see some of these bright points that appear. And if you take observations over the time following this method, you can see that some of these points are actually orbiting the star. This is a real image, and this is a real planetary system where you can see very well the orbits of these points, of these planets. But of course, there are some limitations. For example, let me show you some of the most peculiar, well, not peculiar, but the most of the known of these particular planets discovered with these methods. For example, DH Tauri is a very large planet. It's 3 times the radius of Jupiter, but it's quite far from the star, from the target star. It's 300 astronomical units. Imagine how large have to be the orbital period of this planet. It's about centuries orbiting around this star. And this is the common pattern using this technique. Right now, we are able to find this planet and we are able to see this planet, real see them. These are real planets, but we are limited to a very long orbital period planets and actually also a very large planets. We can still not see inside the coronagraph. Here you can see very well the coronagraph, the shadow that is producing, and we are totally blind to the interior, to the, let's say, the planetary system that is closer to the star. So this technique, while it's very powerful, in the future probably is going to be one of the most uses once the technology is able to make even more efficient masking. This technique still today is working and is providing interesting results. Right now, we can see that it's ideal for measuring the size of the planets, so we can see actually how large they are. It's ideal for finding planets in long orbital periods, as I mentioned, something that is not easy to do with other techniques. So it's a way to explore very cool or icy planets. It's ideal for searching planets in our solar neighborhood. So remember that we need to see the planet. We need to be able to detect the light coming from this planet. So they cannot be very far away. So at the end, they are systems that are, let's say, in our neighborhood. And actually, this is one of the farthest away planetary system detected with this method. And you see that it's just 40 parsecs. So it's just there. And is ideal or will be ideal for conducting follow-up studies. That means that once a planet is detected with this technique, that planet can be studied in more detail with other techniques in complementary ways to, for example, study the atmosphere. This is something that still we cannot do, but will be possible in a near future. So this is making this technique quite powerful, and probably, as I mentioned, in the next decades, is going to be one of the great techniques to detect and characterize exoplanets. But right now, this is the only direct detection method that we have. But unfortunately, fortunately, we have a plethora of indirect detection methods. So we have discovered right now quite a lot of planets, about 6,000 planets, but most of them are actually relying in other techniques, indirect detection methods. That means that we don't see the planet itself, but what we see is how the planet interacts with the lights of the star. So there are several methods here. I'm just describing 4 of them, but there are much more other methods that are, let's say, minor contribution to the detection. So the most important are the radial velocities. Basically, this is a Doppler effect. We will describe a bit more later. We have also the astrometry, that is just measuring how the star is moving in its proper motion. And this loops is coming because it's orbiting with another object, probably a superstellar object, because we don't see the bright of this star, secondary star. We also have the microlensing methods, which is just having magnification of a background star due to the pass by of an star with a planet orbiting, and you can see a disruption of the brightness that is produced. And then we have the transit photometry. This is the other great method to discover planets. This is basically observation of an eclipse. So I'm going to focus in this talk only in these 2 methods, radial velocities and transit photometry. And I have some back slides just in case someone want to learn more about astrometry and microlensing. So at the end of the talk, if you want, we can explore a bit more these ones, but I'm going to focus only in radial velocities and transit photometry. So let's start with the radial velocity methods. So in this particular case, it's important to understand that the stars are not in a fixed point in the sky. Actually, normally, when a star has a planet orbiting it, the star and the planet are both orbiting over a center of mass, a common center of mass. So then the star shows a blue shift indicating the motion of the star towards the observer, and on the contrary, the star show a red shift indicating the motion away from the observer. So actually what we see is a spectral shift all the time due to the movement, the reflection movement of the planet orbiting the star. This is the method that is used by many spectrographs in the world: Espresso, HARPS, SPIRU, Balloon X, NIRPS. There are some of the most famous ones, but there are many others that are measuring this Doppler effect because of this movement. And here in Granada, in our institute, we have the Carmenes instrument, which is installed in the 3.5 meters telescope that is in the Caracas Observatory, and was actually a pioneering instrument using a blue channel and an infrared channel to search for terrestrial planets orbiting M-dwarf. So at the end, how looks like the data set that we have when we use this technique? Well, we have something like this. We have this radial velocity that is being produced by this motion, and we have this k, which is the semi-amplitude. But okay, so this is actually how we can fit this series of data, time series data, where the amplitude is providing with this all this constant, but you see that it's depending on the stellar mass, the orbital period, and of course, since this is an interaction, a gravitational interaction, is dependent on the mass of the planet. So we can obtain the mass of the planet using this technique. But something that we have to take care is that this mass is actually a projected mass. It's multiplied by the sin of the inclination with respect to the observer. So in those cases where the planetary system is not totally in edge-on configuration with the observer, we only can see the minimum mass of the planets. So this is a restriction we have to be aware about. But when we have a very planar system, I mean, something that we can see very well the inclination with us, then this term becomes one, and then we have the true planet, the true mass of the planets. Okay, but which is the typical values for this data set? So for depending on the Jupiter, on the planetary sizes, planetary masses, and orbital periods. Or for example, if we have a Jupiter mass planet in a 1-day orbital period, this value, the semi-amplitude of the radial velocity time series, is of about 200 meters per second. So this is something quite easy to do with our technology, and actually is the first exoplanet ever discovered orbiting a main sequence star. It was this kind of a planet. I mean, actually, I didn't mention, but I can go back. 1 second. Yeah, this time series here actually belongs to the first planet ever discovered by Major and Queloz in 1995, which actually provided them with the Nobel Prize in 2019, Nobel of Physics, because the discovery of the first exoplanet orbiting a sun-like star. So this actually was this kind of planets, the Jupiter mass planets orbiting with an orbital period of 1 day. So imagine 3 decades ago, we were already able to measure this kind of semi-amplitudes, this kind of interaction in between the planet and the star. But of course, everything becomes more difficult if we decrease the mass of the planet or increase the orbital period. For example, the same planet, a Jupiter mass planet, in 1 year orbit, the semi-amplitude is much lower. It's 1 order of magnitude lower. And if we decrease the mass of the planet, and let's say now we are in 1-day orbit, the semi-amplitude started to be a sub 1 meter per second. So regime. So this is actually quite in the limit of today our technology. And if we imagine that we want to observe an Earth-like planet, an Earth mass planet orbiting in a similar orbit that our planet is, in 1 year orbit, then the semi-amplitude is only of about 8 centimeters per second. This is quite difficult. This is right now, these two cases are actually well, this one, Earth mass planet in one day orbit, it can be done today, but this one is quite challenging. And we are now, the community is dealing actually with this because it's extremely challenging. And we are pushing the technology to be able to detect these kind of planets. So this technique is ideal for measuring the mass of the planet, as I mentioned. As you can see here, the dependence of this parameter with the semi-amplitude that we measure in the radial velocities is ideal for finding planets in short orbital periods because it's going to be easier to detect them and will introduce a more effect on the movement of the star. It will be ideal for searching planets in our solar neighborhood again because we depend on the brightness of the star to have a good quality spectrum. So at the end, we need to have this star as close as to us as possible. It's also ideal for conductive follow-up studies because we can, once we detect this kind of planets, we can do many other studies to try to understand better these planets. For example, trying to see the planets in transit, trying to determine the atmospheres, internal structure, etc. And also is ideal, this method is ideal for large scale planet searches, I mean, large surveys. For example, I mentioned before that here in our institute, we have the Carmenes instrument, and we are doing a blind survey searching for planets orbiting M-dwarf. So this is the kind of study that can be done with this. Of course, you can go one by one. Once you know that there is a planet using other techniques, you can go there with this technique and try to measure the masses, but you also can do large surveys searching for planets, let's say, in a blind way. Okay, let's move now to the next detection method I want to talk about today. It's the transit photometry. It's probably the most known way to discover planets, and it's very easy to understand because the concept is very simple. Here, what we have is perfect alignment in between the observer, a planet orbiting a star, and this star. So at the end, at some point during the orbital path of this planet, at some point it's going to block the stellar disk, and then you will see a decreasement in the brightness of the star. So if you are monitoring a star, the flux of a star, and then you have a planet orbiting it and it's transiting, you will see this kind of decreasement in the brightness. This will hint you, of course, it will be a periodic decrease of light. When you have several planets, the structure can be a bit more complex. But if you only see one planet, you will have a very periodic pattern of this decrease of light. This is the typical method or the classical method that used by many space missions. For example, for TESS and Kepler for the NASA missions, and CHEOPS and Plato ESA missions are also using this technique to detect and characterize exoplanets. And it's important here to think about what are the parameters that govern this method. Well, here the important point is actually the ratio in between the size of the planet and the size of the star. So here you have this exemplified very easily to understand. So imagine that you have a star and a planet. So this is a sun-like star, and you see a given planet is producing a certain depth. If you have the same planet, but is orbiting a smaller star, let's say, for example, an M-dwarf, then the relative ratio in between these sizes is going to produce a larger depth in this transit feature that we observe. So of course, it's going to be easier to find planets orbiting a small star than in large stars. And this is just basically because actually what we see just is a relationship between areas and the blocking lights coming from the eclipse. So here you see actually a set of data where you can see real data with planets. So you have two large diamonds here, which indicate the presence of a very large planet, maybe a hot Jupiter, and you can see also some small diamonds. Well, probably it's not easy to see for someone that is not familiarized with this kind of data, but you can see here some small also diamonds that belongs to a smaller planet that is also in this system. So which is the typical transit depth that we can measure. So imagine a Jupiter-sized planet that is orbiting an M-dwarf. This will be a very easy to find or to detect planet because it will produce transit depth of about 5 or 10%. This is quite a lot. This is something that can be done even with amateur telescope. It's very easy to do. If we go to Jupiter-sized planets around a sun-like star, here the depth is still quite large. 1-2% is something that is totally doable with current technology, professional technology. This is totally easy, something easy to do. But if we start to decrease the size of the planet, for example, we now think on Earth-sized exoplanet orbiting an M dwarf, again, we can see that the transit depth started to be also smaller, but still doable with professional telescope. Here we are talking about 0.5% of the light. We see this transit depth is about only 0.5. It's started to be challenging but doable. But imagine now an Earth-sized exoplanet orbiting a sun like a star. This is going to be extremely difficult, but still even possible in the limit, but still possible with transit depth very, very shallow. With professional telescope, large telescope, medium, let's say medium class telescope, we can see this transit depth. It's in the limit of our technology, but it's something that we can do right now. And so, and which are the good points of these methods? So, okay, with these methods, we can derive the size of the planet. And this is important because remember that with the previous method I described, the radial velocities, we were able to determine the masses. So if at some point we can combine both methods, transits and masses, transits and radial velocity, we can obtain the size of the planet and the mass, and then we can obtain the bulk density of this planet. So this is a very complementary method. This is why the community today is actually focused in the combination of these two techniques. This particular one, transit photometry, is also ideal for finding planets with short orbital periods because, of course, when you have short orbital periods, you have more probability to find these planets. So this is why it's an easy method to use. Also, we need to rely in the brightness of the star. So this is going to favor stars that are around our solar neighborhood. So again, we can find planets that are very close to us. It's also ideal for conducting follow-up studies. As I mentioned, if you find a transiting planet, then you can, for example, complement this information with radial velocities, obtain the mass. And then once you have the mass for one side, the size of the planet for the other, you can start to make studies about the internal composition, the chemical composition of the planet, the atmosphere of the planet, and so on. So you can do follow-up studies. And of course, it's ideal for large surveys. As actually I mentioned, that is the technique that is used by many of the space missions like Kepler, TESS, Plato in the future. So this because they can monitor the brightness of many stars at the same time. And then they can see if any of them is showing this decreasement in the brightness and then hint the presence of a planet that is orbiting them. Okay, but I have described these two methods in detail, radial velocity and transits. Briefly only also imaging, and I mentioned that there are other two, that's astrometry and microlensing, which are also important, but still, if you see the number of discoveries along the years since the first discovery in 1995, you see that the two methods that actually are driving the field right now are the combination, well, not the combination, but the radial velocity and transit photometry are actually providing between both the 95, almost the 95% of the discoveries today, with microlensing and imaging much reduced number of detection. So this is why today the community is relying mostly in transit and radial velocity, but in future, I mentioned that for imaging, but also for microlensing will happen. In the future, probably these methods will drive the field because they are able to find planets in a much more peculiar ways. For example, much orbital, longer orbital periods. Transits and radial velocity methods both are favoring planets in short orbital periods, but on the contrary, microlensing and imaging can favor planets on long orbital period, which is going to be very interesting to study very cold planets. Okay, this is more or less what is. I want that you take the message for the methods to detect exoplanets. And now we are going to talk about what we call the great diversity. And this is coming from the comparison with the solar system knowledge. When we compare the solar system with the field of exoplanets, we see now that we can do some statistics because right now we have discovered about 6,000 exoplanets. We can see some trends and we can see some statistics, and we see so many exotic configurations that are totally out of our solar system. So this is telling us that the way of forming planets and planetary systems is very diverse. And this is actually represented with the exotic configuration we find. I'm going to show you some of these strange examples, the exotic worlds that we have found so far. Only a few of them, of course, not all of them, but you will see that some of them are mind-blowing. For example, we have hot Jupiter. This I mentioned already, and probably is the most familiar one because it's very easy to detect. But while they are very easy to detect, actually they are a very low occurrence. I mean, they are not very number in this planet. These planets are a very few, but they are very easy to find. This is why we found very often. But they are very strange. They are orbital period. They have orbital periods shorter than 10 days typically, and the sizes are on the order of Jupiter or a bit less, 0.5 or even a 3 times the Jupiter size, and they are extremely irradiated with a very high temperature. It's not clear how they form. Probably the most, let's say, accepted way to form this planet is like they form a way in the solar in the system, and they migrate inward. But it's still under debate. And actually, many of these planets exhibit a very strange orbit, tilted or even retrograde orbit. So this is a very strange. So this is a very exciting field, the study of hot Jupiter, which has been studied for 2, 3 decades now, but they are entering now in a new era with a very accurate studies about the atmosphere of these planets, and are revealing amazing things. We don't have any of these planets in the solar system. Don't we have also the lava planets? The lava planets are very interesting because they are terrestrial planets. I mean, Earth-sized planets with a very short orbital periods. They are so close to the star that they are in what we call close-in orbits, and these orbits are in tidal locking. That's mean that the rotation of the planet is synchronized with the rotation of the star, and then always one side of the planet is pointing to the star. So this phase is so irradiated, so hot that the silicates are melted. And then what we have in this side of the planet is probably what we call magma oceans, and probably in the other side, which is in the totally darkness, probably what we have is a crust of solidified magma. So this difference in temperature and conditions in between the two phases of the planet, sorry, probably will produce a very exotic climate patterns in this kind of planet. So they are totally exotic for us. And actually, we still don't know if they have atmospheres. It's possibly that they have some rock vapor atmosphere, but also it may be that these atmosphere are totally irradiated and dissipated, and they are fairly, at the end, they are only a bare rocks planet. So it's still under a strong debate. We also have multi-stellar system. So this is actually Star Wars, sorry, for if any of you is a fan of these movies, remember the Tatooine planet with several stars. So this is what we have found actually. We have system with 2, 3, even 4 stars. And the point is that these systems are very complex. If you remember the series of Netflix, the three-body problems, it's totally real. I mean, the dynamic stability of this system is extremely hard. Imagine we are adding even more planets, not 3, but even more components to the dynamical simulations. They are quite unstable and very difficult to explain, but we detect them, and actually we believe that they may be very common, because think that the stellar multiplicity actually tell us that most of the stars born in binaries or even in triple system. So isolated stars is not the common pattern. So it may be very often that have planets with multiple stars, but it's very difficult to detect them because they are a very complex pattern in the light. So we have found right now about 500 of such systems, but we think that they are very abundant. And actually, they can have a very complex path because they can orbit one of the star, both the star, and very other potential combinations. So they are very strange systems. We have also systems that are orbiting Death Star. So actually, the first exoplanet ever discovered in 1992, before the discovery of the Nobel Prize that I mentioned before, it was discovered some rocky planets orbiting a pulsar. The problem is that the pulsar is not a main sequence star, so let's say the race for detecting exoplanet started. when the community start to find planets around main sequence star. But we can find planets orbiting pulsars, white dwarf, and we are not sure about if these planets are the original planets in the system, or actually the original planets were destroyed during the stellar evolution, and then what we observe is actually the recombination of the material and new generation of planets. This is still also on debate. We don't know exactly how this work. We know very few of them, but it could be the common fate of all the known planetary systems we are discovering right now. We also have planets that are orbiting a very young, low mass star, which produce intense magnetic activity, and they have a lot of radiation. So probably these stars are, maybe we are not sure, but they can be erosion, maybe making an erosion of the atmosphere of these planets. And this is interesting because many of the planets we are detecting are planets orbiting these low mass stars, and we are now starting to think about which are the possibilities for this planet to retain an atmosphere due to this intense radiation that we observe. And actually also this intense stellar variability, it's making more difficult the detection and characterization of this planet. So there is a strong community effort trying to make a way to mitigate the stellar activity to be able to see the planets with details. And also we have resonant configurations. A planetary system is said to be in resonance when two or more of its planets have orbital periods that are in a simple numerical ratio. Such a gravitational interaction are regular and reinforce each other over time. So basically, for example, in a numerical example, if the interior planet gives two orbits, the second planet is giving one, 2-1 resonant. But then the other, it can be in resonance with the next. When this planet, blue planet, gives two orbits, the other one in the scale is giving one. So this kind of resonance are very peculiar, and we have found 4 planetary systems with more than 5 planets present in this very exotic configuration. And they are very interesting because they seems to be a very pristine planetary system. They have to don't well, they didn't receive any perturb from the dynamical evolution of the system, so they are like they were formed at the beginning. So they can be used as a laboratories to study formation, evolution, and to tell us about the migration and these planet interactions. Of course, there are many other kinds of resonance, for example, only with 2 planets or 3 planets, but the very peculiar one are when we have more than 5 planets, and we are finding some of them. And the very, and let's say the winner of all the odds planets is the one that we call the free floating planets or the rogue planet, that are planets that actually are not orbiting any star. So this is what we call rogue planet, and are just planets that are floating in the interstellar medium. And it's controversial, their origin. We are not sure if they were ejected during the formation of the system or actually they maybe failed stars. There is also a strong debate in the origin of this planet. We think that they can be very abundant, but they are very difficult to observe and to detect. They actually rely on microlensing technique, which is not always easy. But in the next year, it's going to be a new space mission that probably is going to start finding quite a lot of these planets. And just to give you just an overview of the comparison of the exoplanet field with the current census of exoplanets in the context of the solar system. So here, what you are seeing is the current detection of exoplanet that we know. Here we are representing the planet side, and here the number of planets per star, which normalize and clean it from biases. And you see here that we have some very large planets, giant planets. We have some Neptunes, we have some Earth-like planets. Well, here, as you see, this is in a gray line. This means that we still don't have a very robust statistic for these planets. But if we overplot here in this exoplanet results, the solar system planet, we see here our rocky planets. We have 4 rocky planets in our system, the Earth, Venus, Mars, and Mercury. And then we have a Neptune-sized planet, Uranus and Neptune. And then we have gas giants, which is Saturn and Jupiter. And then we can see very easily that actually these 2 planets are very rare when we see in the field of exoplanets. They are a very low occurrence. And the same happens with Neptune's. Neptune-sized planets are not very common. Okay, for Earth-like planet, we still don't know, but in our solar system, we have four, which hints that they may be very easy to produce. But still, we are having some problems to detect them because they are very small. But we are starting to find more and more. So we still, in coming years, probably we will have more insights about this population. But what is interesting here is that the most common type of exoplanet that we are discovering right now actually are not represented in the solar system. These are two regions that we have here, the super Earth and mini Neptunes. We don't have this kind of planet, and this is a totally a mystery. And actually, it's one of the most striking results coming from the Kepler mission. And actually, here there is a wide variety of possibilities that actually is very confusing for us. Super Earth and mini Neptunes, I write here, show a wide range of possible composition with a highly degenerated internal structure and atmosphere models. And this is what is actually the community trying to understand better why these planets are so common and why and which are the potential composition that they offer. For us, it's totally unknown, and this is one of the great mystery in this field. So okay, once we have talked about this great diversity and the how rare the exoplanet can be, I would like to focus on this example that we recently published. The first one is the WASP 193b. This is what we call the cotton candy planet. And this was a paper that we published last year along with my colleague Hari Barkawi and myself as corresponding author. It was a strong system, very difficult to characterize and to confirm. It actually, you can see that we submit the paper 2 years before the acceptance, and we discovered the planet even before. So it was a long journey trying to understand this planet, the WASP 193. Let's see the details. Okay, in this particular case, this planet was discovered with the WASP experiment. Okay, the WASP experiment is coming from the wide-angle search for planets, which consists in two telescopes, one in the northern hemisphere, in the Canary Island, and the other is in the WASP South, which is in the southern hemisphere. This particular instrument are using the transit photometry method. Remember, it's just monitoring the brightness of the stars, searching for these periodic dimmings in the brightness to see some patterns and elucidate if there is a planet there. So these telescopes, they are very small telescope actually, but wide angle, so they can observe quite a lot of stars at the same time. They were monitoring many stars in the sky, and then following the brightness of this star, just searching for these dimmings that define a planetary transit. So what we observed suddenly in our data was something like this. When we observe this particular star, we detect a dimming in the brightness with a period of 6.25 days. So of course, this was just a radar. It's like a radar, and when we receive this kind of information, then we start all the machinery to confirm the signal. So then, when we detect the signal, we started to observe with more telescope using the transit methods and also using the radial velocity method. So remember, with the transit method, we obtain the size, and here we obtain the mass of the planet. So we combine many different instruments, TRAPPIST telescope, Speculus telescope, and even the space-based telescope. Test observations were also collected, well, not collected, but used in this analysis. And we gather radial velocity measurements from Coralie and HARPS instruments. And as I mentioned, remember with the transit method, we can obtain the size of the planet, and in this particular case, we found that it's a 50% larger than Jupiter. And with the radial velocity method, we were able to measure the mass of the planet. Since now the planet is transiting, we don't have the dependence on the angle. So this is the true mass of the planet, and we found that is half the mass of the Jupiter. If we combine both, of course, you can obtain the density. And here is where fancy things came up. So the density was super low. It was 0.04 the Jupiter density. So if we translate this to a normal unit, so units more familiar with, we find something like about 0.06 grams per cube centimeter, so very low. And this is where all these cotton candy planet names came from, because this is actually the density of this suite of the cotton candy stuff that you can find in first for children's. of course, we never have been there to test the flavor. But it's interesting because when we start to see how this planet fits in the common population of planets, we see here. Well, these are the solar system. We are representing here the density of the planets, and here the planetary masses. And here is clustering the whole Jupiter population. This planet, it actually have the definition of a Jupiter because it has an orbital period below 10 days, and this one is 6.25. So it's a hot Jupiter, is more or less the same state that we were expecting. But the clustering population of Jupiter is about here, and we have the planet here. It's uh, much more light than the rest of the planets. And actually is also similar to Kepler 51b. This is also a very light planet. It's the lightest ever discovered. It was 193b. It's the second lightest ever discovered. But they are a kind of a different planet. This is a Neptune planet and this is a hot Jupiter. So they are a very different planets. But then this planet actually become to the superpuff population. What are the superpuff? So this population of planet, the superpuff, have masses comparable to that of Neptune, but the radii are similar to that of Jupiter. So they are leading to a very low bulk densities of 0.2 grams per cubic centimeter. So all the planets from this point to there are superpuff planet. But if we go even to a more conservative population, we see these planets that are here, that are representing here the DSM versus the planetary density. You see here that we have these planets, and the WASP 103 is the second in the higher position, and also the second one in that direction. So what do we have here? So here we are representing the DSM parameter. What does it mean? This is a metric that we use to tell about the amenability of this planet to be studied, to study its atmosphere using the James Webb. So it's a kind of a very basic metric that tells us about how easy it is to observe this planet with the James Webb. And we see that among the population of superpuff planets, this one is the second one with the highest. At 1 sigma level, actually, is at the same level than the first one. And this is interesting, of course, because it's pointing this as a very good candidate to be observed with the James Webb. And then it's also at 1 sigma level with the same density than the lightest planet ever discovered. So we have that was WASP 103b is the second lowest density planet and the second highest DSM planet ever discovered. And of course, well, among the superpuff population. So this is why it's so interesting. And actually, things are even more rare for this planet because recently there was a study that was published just a few weeks ago where the authors were trying to measure the alignment of the orbit of this planet with the spin of the star. And they found that actually the planet is well aligned. And this is in contrast with what have found with other superpuff planets. The other superpuff planets for which we have some measurements of the alignment, they are all of them misaligned. So it was known at the beginning that the origin of this superpuff planet may come from a very strong dynamical interaction during the planetary formation. But this planet actually is against this theory. So this is a very strange, it's a very beautiful result, but also it's complicating stuff. And also the authors try to explain how this planet were formed, and they say, okay, we can explain this planet using the core accretion model, which is one of the great models to explain how planets are formed, but they need to do fine tweaking to this model. So to explain this model, actually, they have to include more things to be able to reproduce the data. And this is interesting because tell us that this planet is so rare that we need more ingredients in our recipe to make planets. So everything needs to be studied in more detail. And how can we do that? Well, the ideal case will be to using atmosphere studies. I mean, using the technique that is called transit spectroscopy. That means just studying the atmosphere of the planet when it's in a transiting configuration. And if we observe the planet in different wavelengths, we will see this transit that I was describing before. They have different depth. Okay, this different depth is going to tell us about the molecular compounds that are in the atmosphere. And then we can obtain information about which elements are there, and then we can reconstruct the evolution path that was followed by the planet. So This is the goal right now, try to obtain some observation with the James Webb. Actually, my team make a proposal. Unfortunately, we didn't get the time, but another team got the time to observe this planet. So we are very happy with a bittersweet feeling because we know that a team is going to observe, so it's going to maybe solve the mystery about how these planets are formed and this particular one, how it became so strange. But we are not going to be the people who do it. This is the lucky part, the sad part, but still is interesting. Okay, so I have here some list of interesting things that I have mentioned, but very briefly, this planet has some unique properties. It's challenging current models. Later, if you want, we can go one by one all this stuff, but maybe we don't have time to read all of them. And also, this planet has some strong implication to understand better the planet formation. Okay, and very briefly, the other system I want to tell about today is the TOI 2267, what we call the impossible system. This is a system that we submitted a couple of months ago, and we received already the referee report with accepted under minor revision, so we are very happy, and we are just working in the referee report. I lead this study with my colleague Sebastian, and we are finding here a very strange system. Let me go to the details. So this planet was found in the context of the TESS mission. For all of you that are not familiar with TESS, this is a satellite that is surveying the full sky, searching for planets. It's a NASA mission, and this particular star, what we call TOI 2267, at the beginning, it has just an identification number, that is this one here, and was observed by the mission in several sectors. What we call sectors is the period of time that TESS was observing that star. In 19, 20, 25, and 26 at the beginning, in between December and June 2019 and 2020. And this is the typical field of view of this. So what happened here? Well, we have our star here. This is the photometric aperture, and you see that your photometric aperture that you use to build your life curves can be contaminated by other stars. So it's very difficult to really only using test data to really confirm the presence of a planet. You need a rigorous step of processes that you need to do to confirm a planet. But okay, this star was observed during this period, and then the test pipelines ran over the data, and they, let's say, release an alert. An alert is when they provide something like this, TOI 226701. This does mean that this is the first alert for this star, and it was released in September 2020. The alert is coming from a period of 3.49 days, and if we suppose and assume that it's a planet, it will have approximately the size of the Earth. It was quite interesting and then called our attention, so we decided to start studying this star. So the first thing we did is to take the high-resolution images to see which is the status of this star, and we found something unexpected, and is that this is not isolated star, as it was think at the beginning by the test data, but it's a double star, it's a binary system. You can see here two different instruments and telescope that we use to obtain high-resolution images, and you can see very well the central star, that is our star, and then the mirror effects of the companion, which is here. And they are very close to each other. They are separated only a point about 4 arc seconds, which is equivalent to a projected separation of 8 astronomical units. So things started to become interesting. So we decided to, let's say, characterize these 2 stars. And for that, we used fitting, spectroscopic analysis, stellar atmosphere models, and stellar evolutionary models. Of course, this was not done by me because I'm not an expert on stars, but some people in my team are expert on this kind of analysis, and they conclude, or we in our study conclude, that this binary is composed by an M5 and M6 star. And this is very interesting because this is the coolest binary system that potentially, at this point, at this point in the story, the coolest binary system potentially harboring some planets. So it's totally called and catch our attention, and we decided to go for it and start trying to understand better this signal. So the next thing that we did is to, okay, let's recheck the test data. Let's do the process ourselves of searching planets, and for that we use our own pipeline that we have built in our house to search for planets orbiting in transits using test test data, but any other space mission as well as Kepler or K2 or the coming Plato. And we found very well the signal that was released by TESS. This one we found very easily, was there perfectly, but then we found two other signals. The one with an orbital period of 2.03 days and another one with a orbital period of 2.28 days. So that was fascinating because then we were obtaining quite convincing transit shape features in this life curve that was not released by TESS. So, and actually, if you see these ones are actually very close to each other in orbital period. So then we started to think that maybe even if they have a very good shape, and it could be a transit shape feature, maybe they are false positive. We were very confused at this time. So we decided to run some model simulations, and with these n-body simulations, we can reveal the architecture of the system. And if we use the three signals, we assume that they were planet, and they do these simulations, we find that the systems were highly unstable. So it's not physically possible to have the three planets orbiting one of the components of this binary system, because then these two planets collide each other. So then here we make an hypothesis. Okay, maybe any of the signal is a false positive, so any of these are not a real planets, and then we don't have this instability problem. Or the three signals are real planets, but they orbit different stars. And this will be amazing because this never had been found before. We never see planets orbiting the two components and transiting the two components of a binary system. So then everything started to be more and more exciting. So, okay, the process here is just to go step by step and do the validation process, something that is done for all the test paper. So we need to do the confirmation using ground-based observations to see very accurately that the transits are happening in the target star. We also need to search for eclipse binaries, just in case we have the contamination of an eclipse binary in the aperture photometry in the test data, and this is producing the transit that we observe. We also need to search for archival images and to see if maybe there is a background star in the current position of our star. And maybe this is the one that is inducing the transit, and this is also a known false positive scenario. And the last step that we do in all this process is the statistical validation. That means that we take all the astrophysical scenarios that we know that have some transitive parameters inside, binary eclipse system, planet with double the period, half of the period, system that are in the background, many different combinations of transiting things, and we compile the statistical inference of them to see how likely they are in the comparison with the null hypothesis, that is that they are real planet orbiting the target star with that particular period. So we did all this process for all the planets, and we fully validated two of the planets, 1 and 3, this one and this one here. And we found actually that they are close to the 3-2 mean motion resonance, which actually enhance the credibility of this system. And this is very interesting. Also, I will mention later, but when we have here resonance system is telling us about how the system was formed in this configuration that we call normally a migration of this planet that become finally in this particular architecture. And we have a strong evidence that this planet is real thing, the second one, but we still need ground-based confirmation. We have tried quite a lot, quite hardly to try to get the ground-based confirmation of this one, but the transit is very shallow. Is this one here is out of the capability that we have with our telescope right now. We actually got time in the largest telescopes on Earth, the GTC 10 meters telescope, but we were super unfortunate and we have all the time bad weather in all the transits. So we were not able to confirm the transit with this telescope. It was possible to do it because it has the power enough to see the planet, but unfortunately, we had super bad times weather, so it was not possible to confirm the transit. But the rest of the metrics, all of them, make a strong evidence that this planet exists. So if the three planets exist, it means that they cannot be orbiting the same component of the star. And then we go again to what I say at the beginning. Probably what we see here is maybe two planets orbiting one of the components and transiting, and the other planet is orbiting the other. And this is amazing. Never have been found before, and actually have some strong implication on how the planetary system form in very low mass stars. If we go, I'm just almost finishing. If we go to the current census of planets, we see in binaries, we see this is all the hosts that are M-dwarf currently now harboring planetary systems. And we see here that our system is the closest pair of binaries harboring planets. And actually, this actually also has some strong implication about how protoplanetary disk can form this kind of planets. Actually, if you see, this is a log scale, and we have seen here that we are 1 order of magnitude smaller or closer in distance, the projected distance of these two components. So this is really intriguing system. Okay, here I have again also some of the properties of this star, of this system in particular. The unique configuration, we have found the coolest and most tightly bound binary system with planets, and potentially the first planet transiting planets around both stars. This is what I mentioned before. But I'm not going to take into all these details because I already passing from the time. But what I like to say here is that actually this discovery suggests an expected robustness in planet formation processes, something that was discussed quite a lot because we are finding very low planets, very few planets around low mass star. A very low mass star, we know few systems, TRAPPIST-1, Speculus-2, Speculus-3, T-Guardian, and that's all. And here we are finding planets that are formed in a very complicated environment with stars very close to each other. With it's telling us that the disk is still with limited material were enough to make these planets. Okay, I'm going to finish here. I'm sorry for not being able to go through all these points because I think I'm already past the time. So sorry for the time delay. I'm open to any question. Thank you.
Thank you very much, Fran. It was a very, very interesting talk, even too interesting because I have a list of questions now for you, but I will I will first ask people online if they have any question. You can raise your hand or just unmute yourself. Okay, we start then with one. I will start with my list and then if somebody show up.
Okay.
So, Fran, let's start with maybe I lost it, but about the cotton candy planet.
Yeah.
Maybe you said it, but I don't remember. So, what is the star associated with this planet, and also what is the orbital period of this planet? So, what type of how far is from the star?
Actually, you are right, and I didn't mention the type of star. It's an F9 star, so it's a large star, larger than the sun. And the orbital period, let me go there. The orbital period is 6.25 days. So this is why they say that it's in the hot Jupiter population.
Okay, 6 point something days, you said.
Yeah.
Okay.
Okay, let me go here.
And is a more massive star and hotter than our sun.
Yes, the star, yes, is hotter than our sun. It's an F9, so it's a bit larger and a bit hotter than our sun. So it's quite a radiated planet. Yeah, sorry because I didn't introduce the stellar characteristic of this star in the presentation. But yeah, you are right.
Okay.
With a very short orbital period.
Okay, and so it's possible to have with a planet with such a small density orbiting so close.
Well, it's a challenge. I mean, this is what I was mentioning, that this is it's a population of puffy planets, which is, we have some members of this population of super puff planets, but they are not very common. Actually, we only know a few of them. We have other Kepler-51, but it's a different planet. But among the population of Jupiter, we have some, but so, let's say, light as WASP 183. No, this is the lightest one, but still at 1 sigma level, as you can see here. Let me show this picture. At 1 sigma level, you see that these super puff planets are also well connected. So most of them are revealing the population of super puff planets. So yes, they can exist, but we are not sure about how they form. This is still a mystery. It was supposed to be because of the interaction of the planet with another perturber body in the system, and this is coming because the previous studies of these planets found that they are very misaligned with the spin axis of the star. But this particular one is super well aligned. So this is a mystery. And it's revealing that maybe there is many ways to make this kind of superpath planets. We don't know. We only have 4 right now.
Only 4, okay. Well, that's interesting indeed. There is quite of a bestiary apparently of the zoo.
Yes, indeed.
Okay, since I don't see any raised hand, I will continue then. Okay, they are short apparently. Question. Do you know what are the masses more or less of planets that nowadays possible to detect with this micro lensing instead techniques that you just mentioned, or
Yes,
does this
let me check
depend on
here.
the stars?
Well, actually, air mass planet can be detected. Air mass planet can be
Air mass
detected.
planet
So
can detect.
even very small planets. See, let me show here this slide. Okay, okay. Can you see well the microless in the slide?
Yeah.
Okay, here I have actually, I think, okay. I'm sorry because I didn't introduce correctly the the reference for this paper because it was in the back slide. I'm sorry,
Okay.
but this is coming actually for a paper where they were detecting an Earth mass exoplanet. So actually, if you see here the magnification of the brightness of the star that is in the background, if we have an Earth mass exoplanet, it can be of about half of a magnitude, which is actually what you can see here. So actually, yeah, we can detect very small planets with this technique, which is it's fascinating. And actually, it's believed that this technique is going to find quite a lot of small planets in near future and is going to provide super good statistics about the occurrence rate of small planets in different orbits, in short orbital periods and long orbital periods. Something that we cannot do with transits and radial velocities.
Okay, that's interesting. And you said that instead for the radial velocity that so it's possible to detect a Earth-like planet in something like a day orbital period, something like that. But instead for
Yeah.
like year orbital period, you said something like that. The community is now working on that, if I remember correctly.
Yes, let me go to the slide. Okay.
So actually, I have a question also on that. What are the current limitation on that? Is it what do you mean with the community is
Yeah.
working on that? Are we talking about different instrumentation, new instrument, or different analysis techniques, or?
Very good point. Very good question, Caro. Indeed. So here we have the limitation today is in the Earth mass exoplanet orbiting in 1 year orbit. This is the current limitation that we have in both in techniques. When I say technique, I mean the technology and also the algorithms that we use to analyze this data. It's very difficult because actually the stellar activity is quite strong sometimes. At this level, the stellar activity is also contaminating the data, and it's very difficult to disentangle what is coming from stellar activity and what is coming from the planet. So the challenge is double. Here we have the challenge of the technology, which we are increasing, but the bottleneck like we have, actually probably the most difficult part is going to be able to mitigate the stellar activity at this level. And this is one of the, actually there is a Spanish researcher with an ERC grant actually working on this limitation of the particular activity, stellar activity to mitigate this effect on the observations.
Okay, cool. Quite interesting. Thanks, Fran. Thank you very much again. Okay, since I don't see any question, then we'll thank you again for being with us. And okay, so see you everyone next week.
Okay. Thank you very much to all of you and to the organizers and all the people attending today. Thank you.